I wanted to tell you a little bit about sampling distributions for means. What we mean by that is if you go off and take a random sample and ask everyone in the random sample a quantitative question, then you can, one of the things you can do to summarize the sample answers is to give the mean of what that sample said. If we were having face-to-face class, we would do another experiment with dice. And so I was just going to show you what we would do if we had the opportunity to do it. If you happen to have dice in your house, you can certainly do this as well and add your numbers to the mix. But what we were going to do is take a pair of regular six-sided dice and we were going to roll them 18 times, writing down the sum of the numbers that we saw facing up at the end of each roll. So for example, when I rolled them, I have a list here. I first rolled a 2 and a 4, so that would be 6 as my sum. Then I got a sum of 8, then I got a sum of 4, then I got a sum of 6, a sum of 10, another sum of 4, 11, 4, 11, so those are my 18 values that I got. And what you see here on the right is a histogram of those numbers. And we can check that a few of them make sense. I did roll 3 once, and so there's a bar for 3, counting 1 time. According to this, I rolled a 4 4 times, and if you count 1, 2, 3, 4, the biggest roll I got was a sum of 11. Like I rolled a 5 and a 6, and it summed to 11. I did that twice. So you see a count of 2 over here. Anyway, so I had these things pretty spread out. It was a little more common to have the answers right in here than out at the edges, but that's what how the 18 rolls played out. For these 18 numbers, we can put those into one of our web apps to do the numerical summaries or StatCrunch, and if we did that, we'd find that the sample mean 7.1 rounded to 1 decimal place. It's really 7.06, so I'll round it to 7.1. And my sample standard deviation is about 2.6. So that's the mean and the standard deviation of the numbers of these 18 numbers. Now, if we're doing it in class, you all would have gotten a mean and standard deviation, and so we would have made ourselves a nice long list of several different options for these X-bar and standard deviation numbers. So I actually did it 10 times so that you could see there's 10 different answers. Each of these 10 things would be a different person's 18 rolls. So these are the summaries, the 10 summaries of 10 different people each doing this experiment that we talked about up here. What we did in class with proportions, after we did an experiment where everyone in the room got their own sample measurement, their p-hats for that problem, we put them into StatCrunch, and we looked at a histogram of the result. And even that wasn't enough to really see much in the histogram because there were only 16 or 17 different sample proportions to look at. And so if you remember, the next thing we did was put it into a computer and simulated rolling the dice and playing the game. And so I've skipped the step of asking for your numbers to show the simple histogram with just a few numbers, and I've gone directly to letting the computer simulation do this experiment 1,000 times. So again, the thing that's happening 1,000 times is that it's as if 1,000 people are doing this experiment right here, where they roll the dice 18 times, write down what they got for sums each of those 18 times, and then calculate the mean and standard deviation of that experiment. So if 1,000 different people did that, and we put all of their X-bar values, not their S value, not their standard deviation values, just the X-bar values, into a computer and asked it to draw a histogram, I would get a distribution that looks like this. And I'll refer to this as an X-bar distribution. Sometimes I'll call this I won't write X-bar. I usually type that if I don't feel like trying to make the symbol, but X-bar distribution is technically a sampling distribution because it's a distribution of sample statistics. So we'd call that a sample distribution. And you'll notice that that it looks fairly normal, and it does have sort of a normal shape to it. When we were doing the confidence intervals, we said that the shape of something like this may not be really normal. It may be one of these t-distributions that looks mound-shaped and doesn't quite satisfy the right parameters when the sample size is small, and that certainly does happen in this case as well. But we do get this nice mound shape to it. 18 is not so small a sample size that it's not going to look pretty good. The last thing I wanted to point out was when we were doing the confidence interval stuff for quantitative variables, we calculated standard error using a formula that looked like this, sigma over the square root of n, where the sigma is the true standard deviation in the population. But when we talked about confidence intervals, we pointed out that we don't actually know what that sigma is. And if we try to use the sample standard deviation in place of sigma, that's perfectly okay. That's the only thing we have to go on. But you can see how that value is different for different people. It's all more or less the same. It's in the range 2.8 up to 2.1 up to 2.8. And so, we're definitely in the ballpark. But when we say that we're using S instead of sigma, that means we know that this standard error calculation we're doing is just an approximation of the real thing. So if I were to use, for example, if I use the like 2.5, that's pretty typical, 2.5, 2.6. In this problem, so let's just say I use 2.6, since that's the one I got for the numbers I showed you, over the square root of 18. And again, 18 here is the sample size. So it's not just a random number in the problem, it's the letter N in this formula stands for sample size. And the sample here is this. This is our sample. We're sampling 18 numbers and coming up with this sample mean. So our sample size is 18, and then 2.6 over the square root of 18 is about 0.6. In our picture, we can see that that is about right. The center of this distribution is right there at 7. And if I were to go over 0.6, 7.6 would be, wherever it is. So 7.6 would be about there, 8.2 would be 0.6 over again, and 8.8 would be 0.6 over again. And if I go this way, 6.4, go over again, 5.8, and 5.2. And so if we do our normal, the normal thing we do where we write our tick marks in either direction from the center and go up and down by the standard error, then we can see that the empirical rule that we normally use makes sense. Most of those values are within 3 standard errors of the middle, within 3 standard deviations of the mean, and everything else looks about like it does in any other normal distribution problem. One thing to notice is that that 0.6 standard error is a lot smaller than the standard deviation we had up here, and it's not hard to see why. The variability in this picture is pretty great. You can be down here. The minimum value was 3. The maximum value was 11. So there's a wide spread of values among the individual roles, but notice that in the sample means, the X bars that we got, all of those X bars are between 6 and 7. 6 and 8, sorry. All of them are between 6 and 8. And we can see that in the picture, even though when we rolled the dice, we got 3 sometimes and 11 sometimes. there's no way in this X bar distribution that we would ever see an X bar that's as small as 3 or as big as 11. So the X bar distribution has a much smaller amount of variability than the original individual measurements.